Welcome to The Explainer. I am absolutely thrilled you're here today because, well, we have a massive and honestly fascinating journey ahead of us. We're going to travel outwards starting right here on Earth, moving out through our solar system, and then venturing all the way into deep space, literally to the very edge of a supermassive black hole.
Now you might be wondering, how on earth do we get from a dusty launch pad down in South Texas to the edge of a black hole? Well, we build the technological bridges to get there, and today we're mapping out that exact trajectory. We're going to connect the heavy metal rocketry being tested right now, today, to the mind-bending astrophysics that will define our future understanding of the entire universe.
Okay, let's dive into this. Section 1. Meet the Starship V3, Earth and Orbit.
So our journey begins with the historic May 22nd debut flight of SpaceX's Starship version 3. I want to anchor us with just one staggering number, 408. That is the height, in feet, of this mega rocket. It is by far the biggest, most powerful iteration of this vehicle they've built yet. To put that into perspective, the Super Heavy booster, just the first stage, is packed with 33 engines. And this new version is completely decked out with SpaceX's new Raptor 3 engine, which is the sleekest, lightest, and honestly the brawniest Raptor they have ever put together.
And look, they are moving incredibly fast. SpaceX's current rapid testing pipeline is urgently building towards some truly impending, historical milestones for NASA's lunar exploration. Just look at this timeline. Later this year in 2026, they're planning to run orbital refueling tests, which literally means transferring propellant from ship to ship while zipping around in Earth orbit. Then, by 2027, they are targeting the Artemis 3 low Earth orbit docking test with NASA's Orion capsule. And boom, by 2028, the incredibly ambitious Artemis 4 crewed lunar landing near the moon's south pole. Every single test flight right now is an essential step toward hitting those exact dates.
Which brings us to Section 2, Next-Gen Space Tech, Exploring the Solar System. The real question is, how do we actually survive the journey further out? Well, based on the June 2026 tech briefs, we are seeing breakthroughs absolutely everywhere. I mean, we're projected to have 58,000 satellites in orbit by 2030. We're out there actively simulating radio frequency signals on the lunar surface just to make sure astronauts have reliable wireless communication. But what's really going to shrink our solar system? Propulsion and processing. We are looking at dual direct fusion drives by companies like Pulsar Fusion, which promise to drastically cut down travel times with unprecedented power. Plus, the development of silicon-based quantum chips is going to enable totally power-efficient deep space processing. It's a real game changer for sure. And you know, this new tech naturally builds right into mission autonomy. Because as we go further out, communication lag becomes a really huge hurdle. Think about it. Step 1, vast distances cause massive signal delays. Step 2, because of that delay, human remote driving of rovers becomes incredibly slow and inefficient. So, Step 3, we adapt. Generative AI actually takes the wheel. NASA's Perseverance rover on Mars just recently completed its first drives, planned entirely by generative AI models from Anthropic. The AI is autonomously navigating, completely solving that communication lag, and making our operations highly adaptable in those harsh extraterrestrial environments. All right, moving right along to Section 3, the dark matter mystery, journeying to deep space. So what are we looking for when we gaze even further out toward the center of our galaxy? Let's de-jargonize the physics here for a second. You need to know this term, photon shell. Simply put, this is the spherical region outside a black hole where gravity is so intense, so unbelievably strong, that photons, particles of light, are physically forced to travel in unstable circular orbits. It is absolutely crucial, because it's the region that dictates the actual size of the black hole's shadow that we observe from Earth.
And this brilliantly illustrates what happens when we factor in the unseen universe. Supermassive black holes exist inside these massive halos of dark matter. A recent groundbreaking physics paper actually mapped a rotating black hole immersed inside a generalized dark matter halo, and what they found is wild. The dark matter's gravitational pull actually enlarges the black hole's event horizon and shifts this photon shell outward. The solid and dashed lines you're looking at show those inner and outer boundaries expanding compared to a standard dark matter-free black hole. The black line is your standard Kerr black hole, and the colored lines show you exactly how dark matter pushes that boundary further and further out.
Which leads us perfectly into Section 4, Shadows of the Unseen, Visualizing the Invisible. Now, to truly understand these unseen shadows, here is one more essential definition, just to save us all from cognitive overload. The ergosphere.
This is a region located outside a rotating black hole, where space-time is literally dragged along so rapidly by the spin that it is physically impossible for any object to remain stationary. It's like a cosmic whirlpool. You are forced to move with the rotation of the black hole itself.
Now, what's really interesting about this slide is how we can essentially visualize the invisible. Over on the left side, we see the geometry of that ergosphere, and on the right, the resulting shadow of the black hole. Notice how, especially at the higher spin rates in the bottom charts, the shadow isn't a perfect circle anymore. It's this distorted D shape, all because of that intense space-time dragging we just talked about. But look closely at the colored lines, which represent the dark matter density. The dark matter actively alters the geometry of the ergosphere, and it visibly pushes the shadow's boundary outward compared to the standard model shown in black. There's a specific parameter in the math that controls the inner density cusp of the dark matter, and it has a profound effect on stretching the shadow we actually see.
So the absolutely crucial point here is this stark contrast. A standard Kerr black hole assumes a constant mass parameter, which gives us a predictable circular or D-shaped shadow. But a dark matter immersed black hole, it has a modified mass function because the halo's mass accumulates with the radius, and that leads to enlarged horizons and a highly distorted shadow shape that completely depends on the halo's density. Now, why does this matter to us? Because astrophysicists are, right now, using actual Event Horizon Telescope observations of Sagittarius A star to constrain these very dark matter parameters. By measuring the exact size and shape of that shadow, we can calculate the density of the unseen dark matter sitting right in the center of our galaxy. It's just brilliant.
Which finally brings our journey full circle. As we analyze these mind-bending cosmic anomalies, I really want to leave you with this final thought. The immense tools we build today on launchpads in Texas are the very vessels that will one day let us physically reach the anomalies we can currently only see as shadows. From the 33 roaring engines of a Starship V3 to AI navigating the dusty Martian surface, all the way to telescopes measuring the gravitational footprint of dark matter, it's all one continuous, breathtaking journey of discovery. But honestly, it leaves us with one massive question. When our technology finally allows us to reach these cosmic shadows, what else is going to be waiting for us out there in the dark? Thank you so much for joining me to explore this incredible material today. Keep seeking, keep learning, and I'll catch you on the next explainer.